Compared to humans, computers are fast. Even a really old junker laptop that barely runs would most likely be able to solve a math problem faster than you can. In fact, some would say that it instantly computes the answer. However, we know that instantly, as in no time at all, is physically impossible. Depending on your machine or programming language, etc., adding two numbers together may take somewhere around 1 nanosecond. We can very roughly define a simple action, such as adding or subtracting, accessing or modifying a variable, or even a simple combination of those actions as one operation. While the time can vary a lot between operations, big O notation is generally used to estimate the runtime of our code, which usually lets us get away with this oversimplification. Now actually onto big O notation. In the context of computer science, big O notation is mainly used to describe how much time and memory a program will take. For example, let's say we're given this problem. Given n, then given n numbers, output the sum of all n numbers. Simple enough. We could create a variable and store n inside it. Then create a new variable which will hold the sum. Then loop n times and add the new inputted number to the variable, which holds the sum. And finally, output the answer. This solution can be described as having an O runtime and taking up O memory. The idea is that as n increases, so will your amount of operations. So for example, if n was 1 million, you would have to take a new number in as input and then add it to your running total 1 million times. Therefore, 1 million operations. You might have noticed that despite the fact that we need two variables, one to store the value of n and then another to store the running total, space complexity is still described as O. This is because that big O notation, at least in computer science, is roughly used to show how time and memory needs of a program increase as its constraints increase. In fact, big O notation actually drops constants. So for example, O3n is equal to On. This might make a bit more sense if we graph it out. Here you can see a linear On runtime compared to a constant O1 runtime. The O1 runtime will always take the arbitrary amount of runtime, regardless of what n is, and could be 1 trillion, and O1 would still be the same. However, this would not be the case with On. This is why O2 is simplified as O1, because as n approaches infinity, the number of operations, or bits of memory, will stay the same. This is also the case for O2n being simplified as On. While O2n will have a steeper line and therefore increase faster, it still is generalized as linear. Let's pretend you get a new hypothetical problem from a teacher, and you and your classmate are sharing a computer. The problem is as follows. Given integer m, output m times 14. M can be at minimum 1 and at most 1 trillion. This should be no problem. However, let's also pretend your keyboard is broken and you can't type in an asterisk, thus disabling your ability to multiply. Not to worry though, your friend has a simple solution. Multiplication is simply just adding, but many times. They create a variable and then add 14 to it m times using a for loop. Your friend is certain that this workaround will be unnoticeable as computers are fast. However, once you test the program by entering in very large numbers, you quickly realize that it is taking too long to run. In this situation, you could use big O notation to analyze the code's runtime. Your friend's code would have a time complexity of OM. This is too slow, as assuming that the computer would work at one operation per nanosecond, in the worst case scenario, where m is 1 trillion, it would take more than 15 minutes to run. However, despite the fact that you cannot use multiplication, most of you probably see the faster solution, which is use a for loop to add m to a number 14 times. This solution is actually O1 time, even though at one operation per nanosecond, this would take 14 nanoseconds. While this example has an obvious slow solution and fast solution, future problems may not be as straightforward. It's also important to recognize that technically, given infinite time, both solutions are correct. This is where time limitations in competitive programming come into play, and they may restrict or hint at certain solutions. Also keep in mind that most good problems will use the upper limit of their constraints, so you must have a solution which can handle the worst case scenario for full points. The last thing that you should know is that the upper limit for most modern judges is 1 billion operations in 1 second, assuming you're using C++. If you're using Java, assume somewhere around 100 million is the upper limit. For Python, assume less than Java. And in general, 10 million operations is usually a safe number. So for example, if you're given 2 seconds of runtime and you know that your program will take 1 billion operations in the worst case scenario and it is written in C++, then your solution should be fine. And that'll be all. Thanks for watching.